In this video, we're going to be talking about motional EMF, not to be confused with emotional EMF, but that's the kind of thing we're looking at. This is going to be related to Faraday and Lenz's law, but a slightly different idea. And an interesting result of it is the magnetic damping effect, which if you were in class on Tuesday, you got to see some examples of. So motional EMF, the basic idea is if you move a conductor in a magnetic field, you know that conductors have charged particles, and the charged particles can feel forces and move around in there. And if you provide a conducting path, then, current could flow. We already know how to figure out that part of it from Faraday's law, right? So if it moves with a constant speed in a uniform magnetic field, Faraday's law tells us that if we can calculate the flux change, the rate of flux change, we can figure out how much EMF there will be. We use this flux formula, BA cosine theta, or integral of B dot dA, and then we get an EMF. Once we have an EMF, right, we can figure out, using all the dimensions of this, everything we need to know. We can find out that we get L, that distance, dx dt, gives us the area, and that gives us negative BLV. Which is an interesting formula. So that means the speed of the rod times the length of the rod times the magnetic field strength gives us the magnitude of the EMF. So we have the changing area formula from Faraday's law, but now we also have this one that's just focused on how fast you're moving the rod and the dimensions of the setup. And this we call the motional EMF. It is still the same EMF that you would calculate from Faraday's law, but because we're using the motion of the rod to calculate it, we give it a slightly different name. So 2 questions. What is the current direction and how much current flows? Well, you have 2 ways to think about the current direction. One of them is Lenz's law, which we already know, counterclockwise by Lenz's law. The other way you could do it is by using the right-hand rule. If you think about the rod moving to the right and positive charge, or in the magnetic field in, a positive charge would be pushed up toward the top of the rod, and conventional current flow follows positive charge, so it would go around in that loop. And then when it comes to how much current flows, this is using Ohm's law. Take the EMF we calculated and divide it by the resistance of the wire, whatever that happens to be. So there's some interesting questions here. Like, you get current to flow. That's exciting. We can do useful things when current flows. We have an EMF and we have current. So we have charge moving, we have a voltage, we have energy. Can we just get this? If these are frictionless rods, if we give this a push, will it keep going forever? Well, let's think about this. The rod has current flowing through it. And by definition, magnetic force acts on things that have current flowing through them. And if you use your right-hand rule for that one, current up, B field in, you're going to get a force backwards, pulling you back to the left, opposing the motion. And so that means that if we want to move the rod at constant speed, we're going to have to pull it, apply some force to keep it moving at a constant speed. Whatever that magnetic force is at the speed that we want with a particular current, we're going to have to pull with that same force to keep it moving. And if we wanted to accelerate it, we would need a bigger force. But of course, as you accelerate it, it's going to go faster, and then the magnetic force is going to grow as well. So it's not a free thing. This is not free energy. So we can think about this in terms of taking a coil or loop of wire, putting it in a magnetic field, and pulling it out of there. The magnetic force is exerted on whatever part of the current is in the field and not on the part that's out of it. The top and the bottom are going to have opposing forces, right? Because one's to the left, one's to the right. And so the magnetic force, one will be up, one will be down. So no net force from the top and bottom segments, but from the left-hand segment where the current is going up the screen, we will have a magnetic field opposing, or a magnetic force opposing the motion. And this will be true no matter how you go about thinking about this. The magnetic force is always going to oppose the motion, which is good. If it went with the motion, you'd have free energy. You'd give it a little pull, and then it would accelerate, and that doesn't make sense. This effect is what we call magnetic damping, and it's easiest to think about in terms of a coil of wire. If you're trying to pull it out, having that opposed. But it works for anything moving through a wire. Examples of this are the variable gap magnet and letting something go through it. Triple beam balance. If you look at the edge of the far end of a triple beam balance where it goes up and down and kind of points at the little line, you'll notice it doesn't just jiggle around rapidly, it kind of moves slowly. And that's because there's a piece of metal there and some magnets on the side of it that provide this magnetic dampening. So the faster it moves, the more it tries to stop it. If it's moving very slowly, it can settle to its final position. And the magnets don't do anything to it when it's not moving. Another way to think about this is in terms of power and energy. How much power is required to maintain this constant velocity? Well, if you remember back to our mechanical energy discussion, power is the applied force multiplied by the velocity. And so we can figure that out, right? The applied force is equal to FB, which is ILB, which is all of this. So we end up with B squared L squared V over R, which, is an answer, where R is the resistance of the circuit. So the power required is B squared L squared V squared over R. Okay. That's not necessarily very intuitive. However, if you think about electric power, which is, I times V, or V squared over R in this case, the EMF is BLV, square that, divided by R, the resistance. And that is the exact same thing. So whether you go about this in terms of mechanical power based on the motional EMF and this damping force, or you think about it in terms of electrical power, you get the same result, which you should. So that's good. What about energy? How do we think about this in terms of energy? Well, oh dear. Sorry about that. Maybe I'll cut that out. What about energy? The kinetic energy of the rod is not changing. So it's constant kinetic energy. And we know that net work on something is equal to the change in kinetic energy. So this implies that there is no net work, right? Or that the energy is not increasing or decreasing. And so what's basically happening is, because there is an electrical current running through a material that has some resistance, the wire, or we could add, say, a light bulb and actually see the light and heat effects or experience them. It's dissipated as heat. That's what you're doing, right? You're opposing this motion. You're applying a force. Where is that work going? Well, it's turning into something else. What happens if we let go of the rod? So this one, obviously, you're not going to answer this question, but this gives you a sense. If you were to let go of the rod, it's moving at some speed, and there's a magnetic force opposing it. So it stands to reason that A or C will happen. It will slow down because there is a magnetic force opposing motion. That means it's going to have a net force opposite its velocity, which means it will have a decreasing velocity. Okay, but which of these makes the most sense, right? Will it decrease at a constant rate? Well, it will not, because that implies that the net force, would be a net force is constant, a constant acceleration. But we know that the magnetic force depends on the velocity. So as it slows down, the net force will get smaller, and therefore the acceleration rate will be smaller. And so that's why C is actually our best answer. The faster you're going, the bigger your rate of change, the bigger your net force. And at the end, you're approaching zero. And again, this is why the magnetic dampening effect is so useful for that triple beam balance. If you're going fast, it puts a lot of force to keep it from rattling around. If you're barely moving, it doesn't apply much force at all to gently bring you to rest. So this relationship, the speed that you are traveling, or that an object will be traveling due to this magnetic dampening, if you just give it an initial speed and then let it go in the field, looks like this. It's this e to the negative t over time constant, which should be familiar at this point from capacitor circuits. And we need to swing back and look. This is actually how air resistance and drag works as well. So we want to find this time constant so that we can look at it. The derivation you don't need to be able to recreate, but I'll walk you through it. If you think of the net force as the mass times the acceleration, ILB is that net force, I is BLV over R, acceleration is dv dt. We can set up this equation, separate the variables and integrate, limits, et cetera, get rid of the natural log, and you end up with that equation. Now, again, you do not need to know how to do this. You just need to know that anything that follows this kind of damping or decay relationship, like the time constant, that has the time constant like this, like in RC circuits, or drag force because of air resistance, or the magnetic dampening effect. Inductors behave this way as well, which we'll talk about soon as we finish up our year all behave in this way. So it's all the e to the negative t over tau, or 1 minus e times e to the negative t over tau, depending on if it's approaching a final value or decaying toward 0. So that's the idea here behind the motional EMF and magnetic damping.